I'll start every class, so if there's something from the homework you weren't sure on or you want to talk about, just fire them out and we'll take them one at a time. Luca.
Well, for, like, the video, what's it called? Like the lecture video, was that supposed to have sound?
Yes.
I don't know if it was just me, but I didn't have sound.
Uh-oh.
That's scary.
That's weird. I hope that hasn't happened every time. Let's see.
So section or chapter?
Yep, just you. Just you. That's a relief. Woo! It's not Will. Which, no, Will.
Did you do number 3?
3, yes, sir. So just drop these in here. Yeah, this would not be a function. That should be the result that you get. What I would probably do here is try to rearrange it to get the y by itself. So I'll divide both sides by 2 and then square root both sides to get the y by itself. Remember, when doing that, what do we have to remember? Plus or minus.
I wrote the question wrong.
Oh, well, that would also make it hard to get the right answer. So if we went to go graph this, then we could do x over 2 in one line and then negative x over 2 in the other line. And I'm going to just do zoom standard because I use my calculator all the time and mess around with the windows, and it's probably not where I would want it to be anyway. So that always just resets it to the normal window, and look at that. Is that a function? No way, Jose. Right? Fails the vertical line test. Yeah, about 100 different times. Actually, infinitely many, even more than that. Whoa! Cool. Anybody else questions from homework? Yes, Hunter. 8? Sure. Ha! Somebody's a comedian here. All right. So 8. So when I look at the domain for this, I notice, okay, I want to think about the operations involved. So I have, what do I see? I see division, I see squaring, and I see subtraction. So if I square a number, I always get another number back. No issues there. If I subtract 2 numbers, I always get another number back. No problems there. If I divide 2 numbers, I can get into trouble there. There's one number that I have to worry about, and it's dividing by 0. So my domain is going to be then everything except where that denominator can be 0. Okay. So I'm going to just kind of solve this this equation. So what do we want to do to solve this? Yeah, go ahead.
Add 1.
Okay. Joey says we're going to add 1 to both sides. And then square root both sides. Sure. And when we do that, what do we have to remember? Plus or minus. The square root of 1 is just 1. So I have 2 answers then, right? Okay. So let's kind of think about, it wants a domain. So eventually this is going to go into interval notation. So let's draw a picture of what not equal to plus or minus 1 would look like on the number line. Well, I know that we can't equal 1 or negative 1, right? But everything else would be okay. So when I look at this, then, it looks like 1, 2, 3 intervals that I'm going to have to write for this. Is that okay with everybody? So I'm going to take that first interval. It contains the arrow pointing to the left, so I know that's negative infinity, and it ends at -1. The infinities always get a parenthesis when we write our interval notation. -1 has an open circle on it, so that's going to get a parenthesis on it. And then I'll do the union, and then I'm ready for the next interval. The next interval starts at -1 and ends at +1. Both of those have open circles, so they're both going to get parentheses. And I'll do my little union symbol, and I'm ready for the last interval. That last interval starts at 1, and it contains a arrow pointing to the right, so that's going to be positive infinity. The 1 has an open circle, it gets a parenthesis. Infinities always get a parenthesis. And there we go. Yes, sir. Sure. Hunter, you happy there? Okay. 7. Same idea here on 7. So if I go and I look, the only operation going on here is division. I know division is a problem if the denominator is equal to 0. So I just have x cannot equal 0. Well, there's nothing to solve there. That's my statement. So if I kind of draw my number line, I'd have an open circle at 0, but anything else is okay. If I look at that, it looks like I have 1, 2 intervals that I would need to write. So the first one, I have the left arrow, so that's negative infinity, and then we stop at 0. The infinities always get a parenthesis. The 0 is an open circle, so that gets a parenthesis. Then I'll do my union. And the next interval starts at 0 and contains the right arrow, so that's positive infinity. And both of those, again, get parentheses. And that's where we're at. Luca.
I'm kind of confused on how we're getting the x does not equal 0.
Okay. So when you divide two numbers, the only division problem that'll get you not a non-answer is if you divide by 0, right? So what we're saying then, the domain is all of our numbers except where we divide by 0. So I'm just taking the denominator and setting it not equal to 0, because that's the only division problem that's going to won't give us an answer. Does that make sense?
Yeah, could you do like number 5 then, for like one that's not a division?
Sure. Yeah, let's do 5. Okay. So number 5, the only operation going on here is subtraction, right? If I subtract two numbers, do I always get an answer?
Yeah.
Yes. So that just tells me that my domain should be all real numbers. How do I write all real numbers as an interval?
Infinity.
Negative infinity to positive infinity. That's just everything.
So
We don't get any problems because I can always subtract two numbers. Any number works.
So is that the same as 6?
So the same thing with 6, right? So 6 is squared in subtraction. We can always square two numbers. We can always subtract a number. Subtract two numbers. We can always square a number. So again, there's nothing that causes a problem. The domain should be all real numbers. Yeah, exactly right.
The same answer as 5.
5 and 6 should be the same, yes. Now all the seats all got jumbled around. I'm not sure what is your AJ? Thank you.
So you have to, the first thing you need to do is look for if there's going to be a problem,
The operations involved, yeah.
if it's not, then it's always all real.
Correct. Yeah, you start with the assumption that it's all real numbers, and then it's like, oh, but what problems could I have? And if there's division involved, well, the denominator can't be 0. If there's a square root involved, the stuff under the square root can't be negative. If there's, something else, then, you might have more. Yes, sir.
Number 9.
Sure. So we'll do 9 here. Okay. So the operations that we see involved are subtraction, no problems with that, and the square root. Now I know that I can't take the square root of every single number, right? If I take a square root of negatives, I get imaginary results. So I don't want that. So I don't want the part that is underneath the radical to ever be negative. So I'm just going to say that has to be greater than or equal to 0. So I'll just add 1 to both sides of my inequality. And if I put this on the number line, I have a filled in circle at 1 and then pointing to the right. So I have just one interval here. It starts at 1 and it goes to positive infinity. The infinities always get the parenthesis, and since I have a filled circle, the 1 should get a bracket. Sure. That's the next set, right?
Can we do 1 through 100?
I know someone wants to make that. I want to do number 6.
Okay.
So not 6. I'm
You already did 6.
not 6.
All right.
Dude, we probably already did.
So here we're asked for the range, right? Range is always going to be more difficult than the domain because it depends on the domain. Now, for this level of class, my suggestion to you is let's graph this and look at the picture. And we're going to use the picture to kind of come up with our range. The domain we should be able to do algebraically. At this level of class, I would not expect you to be able to do the range algebraically. So let's take a look here. We have x squared minus 4. If I graph that, I get this parabola. It's a function, absolutely. I knew that though from the directions, right? It tells me it's a function there. But that's a great observation, right?
Yeah.
All right.
I was excited.
So the range is the y-coordinates, right? So what I'm going to do is I'm going to locate the lowest point on my graph, which appears to be this one right here. What do we call this point on a parabola? It has a name, right? It's a minimum, but it also has a special name that's applicable to just parabolas.
What does it start with?
V. Vertex. Yeah, that's the vertex of the parabola. So if I look at my graph, that looks like the point 0, negative 4. Everybody agree with that? So my smallest y-coordinate, or the lower bound for my range, should be negative 4, right? And if I plug 0 in for x, I can see that I would get the y-coordinate negative 4. Everybody see that? So the point 0, negative 4 is actually a point on my graph. So that tells me that I should have a bracket here because that's a y-coordinate that actually exists on my graph. And the smallest one. Is everybody good with that? Let's go back and look at our picture again. Now I'm going to look for the highest point on my graph. Yeah, so I have the arrow going up, so it's going to infinity. So there we go.
Nice.
And I'm done. Because it's a continuous function, all the y's in between those are covered. So I just need to worry about the highest and lowest points. And that'll do. You guys cool? Sure.
I want something.
We're doing
all of them.
Yeah.
X minus 3.
Why are they making fun of me?
Yeah, let's look. We'll do it together here,
I
right?
think it's a great question. Yeah.
Okay. So do you see a lowest point on the graph?
Can we try to do it?
Yeah.
Sure, try it. Grab your calculator, give it a shot. Or just look at what I've written down. Take a minute to think about it. We'll tell you the answer in like a minute or something, right?
This line
It's a function. It says that
it is a function. We knew it was a function.
it's a function.
Yes, sir.
I think something's up to my calculator.
Okay, come show it to me.
I have two of them if you need one.
Every time I
Go all the way down.
I
grab
stay ready.
something.
Hey, I stay ready for math.
That happened to me.
Okay.
It's the lowest point of the
So we're just going to solve it this way. Oops. So I'm just going to do zoom standard.
You need a second
Problem
one?
solved.
I have a second. All right.
So it was saying error window range. So you probably had something screwed up here on the settings for your window.
Okay.
In that case, I just do zoom standard. It just resets the window back to the default, and that usually clears any kind of issue with that. No problem.
Dude, I'm trying to tell you, how do you know it's positive? You have two? How do you know it's positive?
So that's three.
Uh-oh. That was our 1 minute. I love the timer. It scares kids every single time. It's like the fire alarm. All right. So if I look at the graph, I'm going to start by looking for the lowest point on the graph. That appears to be this one right here. Everybody agree with that?
Yes.
If I count over, that looks like the point 3, comma 2. So that would indicate to me that 2 is probably the lower bound for my graph.
Oh, and it goes to infinity.
What I want to do next is I want to determine is 2, should that get a parenthesis or a bracket?
Correct.
Great, because if I plug in the point 3 for x, 3 minus 3 is 0, square root of 0 is 0, 0 plus 2 is 2. So there's definitely a point on the function that has the y-coordinate 2. And then I'm going to look for the highest point on my graph. Well, it looks like it's going to keep kind of going up and to the right forever. So once again, that's positive infinity. And I'm donezo's.
I understand. A lot of sense.
So again, for you guys at this level, doing the range just by looking at the picture is perfectly acceptable, right? That's good enough.
How do you know if it's a bracket or parentheses?
So what I'm doing here is I'm looking to see, is there a point that has the y-coordinate of 2? Right? So I noticed if I plugged 3 in for x, 3 minus 3 is 0, the square root of 0 is 0, 0 plus 2 is 2. So the point 3, 2 is actually a point on my function, right? So that's how I know that 2 should have a bracket, because there is a point whose y-coordinate is 2. That's all I'm checking. Because sometimes it's hard to know, is that very first point, is that like a filled in circle or is it like an open circle on my graph? Because the calculator's not going to really show that, right? It's hard to tell. But usually if you have the equation, it's pretty easy to see often like how to get that. Because in each of those it was like, okay, just this extra part appears to be what I need, so everything else just has to turn into a 0, right?
We do number 10. Oh.
It's the last one.
Sure.
This one's confused a little bit.
Nah.
Sorry. I just want to understand.
Yeah, I get it. What letter is this? H. All right. So the operations that I see subtraction. Does that matter? No. I see division. Does that matter?
Yes.
Yeah.
Okay, so the division says the denominator can't equal 0. And I see a square root, right?
Plus minus.
So the square root tells us that the stuff under the radical has to be
Greater than 2.
or equal to, right? Because we can still take the square root of 0. That's okay. So we have both of these two things going on.
So the square, if it's division, it's basically can't equal 0.
The denominator can't be 0.
Denominator. And then if it's the square root
The stuff under the radical
under the radical.
has to be greater than or equal to 0.
So, okay.
Non-negative
Okay.
is the words, but okay. So if I look at this first equation, I'd square both sides to get rid of the square root. And now I would really just combine these two together. If I have something that's not equal to 0 and greater than or equal to 0, well, that's just really greater than, right? If it's greater than or equal, but it can't equal, well, that's just greater than is all that's left. Okay, well, that's easy enough. I like that it got down to one interval here. And I'm done. Does that feel okay?
Yes.
Sure, no problem. I don't know that there's anything more to ask about from the homework, so let's go ahead. Return to the to where we left off. Let me pull that up for myself. All right. So 1.3 is about continuity. So when we talk about continuity, this is another adjective we can use to describe a function. So we say a function is continuous if we can draw its curve without having to pick up our pencil. Right? So if I can do whatever and draw it without having to lift my pencil, that's continuous. If I have to pick my pencil up at any point, that tells me that there is some type of discontinuity in the graph. So let's talk about the types of discontinuity. Continuity. So we have the first type is an infinite discontinuity. In Algebra 2, you guys also refer to these as vertical asymptotes. You could use those two terms interchangeably. Let's draw a picture and kind of refer to or remind us what that's going to look like. So usually when we draw a picture of a infinite discontinuity or vertical asymptote, we use like a dashed line to represent that. And that'll look something like, oh boy, that was weird. Must have touched something. Looks something like that, right? No way I could draw that curve without lifting my pencil because it basically breaks into two different pieces like that. Everybody's okay with that? Notice that I have 4 arrows on a situation where I have an infinite discontinuity. I have 4 end behaviors. That's what we call the arrows on your ends of your graph. Okay. The next one we have is what's called a removable discontinuity. So for a removable discontinuity, we just have something like this, where you have the whole curve except for one point that's missing. So there's just like a little gap in our graph. Right? And I think we looked at maybe we didn't do that yet. I get confused. I have this class on 2 separate days, so I get turned around on what I've done when. You know what I mean?
We didn't do this.
Okay. And our third type is called a jump discontinuity. So let's say that maybe we have something like this, where the graph goes, half of it ends, and then it just like moves up or down some amount, and then starts over doing, something else. It's like the function is jumped, right? Like we just chopped it and then like put it somewhere else. Everybody's okay with the vocab there? Luca?
Yes. Does the like you kind of made like an open dot and then a closed dot
Mhm.
and a jump? Is that like?
Yeah. Yes. So could both of them be open and still be a jump? Yeah, that'd be okay. Could both of them be closed and still be a jump?
Yeah.
No. Why not? Why could not both of the circles be closed?
That would make it infinite.
Nope.
They would, if they were both closed.
Yeah, if they were both closed, why is that a
They're on
problem?
the same,
Vertical line. So it would be
Oh, it's not a
That would
function.
be-
no longer be a
It's not a
function.
function.
Yeah, there you go. You got there.
That's not a function.
Vertical line is failing right there.
So you guys cool?
Yeah.
Yeah. Great. I like that question because I could wrap it around and bring it back to something we just got done talking about, right? All right. Let's look at a couple of examples. This is just going to be something we'll do on the calculator. So let's just say we have f of x equals 2 over x squared minus 4. And we're just going to look at the graph and decide what type of discontinuities they have and where they're at, right? Okay, so I'm going to start just by typing this into my calculator. Anytime I have to type something in that's a fraction to my calculator, I like to use the fraction command. The easiest way to access that is to press alpha, y equals, and then choose the first option. That'll get you that horizontal fraction bar. That's really convenient because to get that thing that I've written down typed into my calculator correctly is I need a whole bunch of sets of parentheses. Or I can do it this way, which I can type it exactly like it looks on the sheet of paper, which is way easier.
Oh,
Yeah, let's go ahead and graph now. Yep.
yeah.
I see how many infinite discontinuities?
This is weird looking.
I see 2. I see one right here. And then I see another one like right there. You guys agree with that? Okay. So let's look at the locations of those.
They all look vertical.
Why do you say that?
Because they both top lines are they not connected? No.
They do not connect to the way down.
Well, there's 3 different lines right
Yeah, there's 3 different curves. Yep.
If there's lines, and there's only 2 spaces in between them.
Yep.
It's a space in between.
Yeah, so let's do this real quick. I'm going to turn off the axis. And if you look, there's one gap here and one gap there. Those are your 2 discontinuities. Even though there's 3 pieces of our graph, there's one gap and one gap.
It's not a big gap. What's that?
So if there's an asymptote, it's a
Separated
infinity, basically.
It's an infinite discontinuity. Yep.
Using the line right here. Line right here that goes down. The line separating this. Yes. And this line separating this. Those are 2 S's. Oh, okay.
Okay. So The other thing we should include here is the location of these two infinite discontinuities. So I'm going to look at my graph, and I'm going to look at where that gap is, and I'm going to describe it using the x-axis. So it looks like at x equals -2, if I count over 2 units, and I draw the vertical line, that looks like the location right there. You guys agree with that? And if I do this similarly on the other side, if I count 2 over, it looks like x equals 2 is the other vertical line location. What do you notice about the values -2 and +2 with respect to the equation of this function? What am I going to get if I plug either of those numbers into my function?
0.
A 0 denominator. So your discontinuities, one way to generate one, or them, is the numbers that give you a 0 denominator. Everybody okay with that? Okay. Let's do another example right quick. Okay. So let's do that one. So try typing that in and taking a look and telling me what you see. Oops, did I type that in right? Oh, shoot. That's supposed to be a -6, not a +6. Sorry. Like that didn't look like I wanted it to. There we go.
Alright, keep going, Bo.
Okay, do you see a discontinuity here?
No.
But is there a value for x that would cause the denominator to be 0? -3, right, would make a 0 denominator. Well, let's maybe zoom in, because obviously there's not an infinite discontinuity there, but maybe there's a removable. Everybody's okay with that? So I'm just gonna look at that. So that looks like -5 down there. So we'll do like this. We're gonna do a little less than -3. A little bit more than -3, and then we'll go right around like -5. I'm just going to reset my window and just take a look and see what I see. Oh, look at that. It's really little. If you look at your own calculator, you'll probably see it better than on the board, but there's a little tiny gap there, right?
How do you do like the exact?
I just changed the window to like what I want. So I just changed the window to something a little less than -3, a little more than -3. And I estimated that to be like the point -3, -5 was what it looked like from the big picture. So I changed the Y's to just make sure I could see what I was looking. You know what I mean? You could just use you can use the zoom in command also if you center it at, around -3, and you'd probably get there too. I want control, so I like to pick my own windows, Anyways, that was the window that I used, and I see the gap there. So that one is the removable. And again, that's at x equals -3. Okay. Yeah. So if you just press zoom standard, so you press the zoom button and you pick standard, it'll take you back to the normal window. That's the easiest way to get back to your usual window, is just to zoom standard. If you're ever having trouble getting a picture, that's usually a good place to just, let's go back to normal, and then I can mess with my window again.
Since that one isn't under the, since that one isn't squared, it would only be negative. It couldn't be positive.
Correct, yes. Because positive 3 would not give us a 0 denominator there. Very good. So, again, the point of what we just did, when we initially graphed that, you're not going to be able to see a removable discontinuity, right? But the fact that I had a denominator that could equal 0 was the thing that hinted like, oh, maybe I should go hunting for a removable. Let's go check where that would, where the denominator is 0, see if there's something there. And we did, we found it. There's just a little tiny gap. Little bitty guy. What do you guys think? It's all right?
Good.
That was
Feeling
good.
good on this.
Good. That's about the gist of what I'd want from you guys with continuity and discontinuity. So next thing we're going to talk about is increasing, decreasing, and extrema. Again, what we're doing right now is just coming up with like adjectives to help describe our functions, right? So we can talk about whether our function is continuous, and if it's not, where the discontinuities are and what type they are. We can talk about, we'll be able to talk about whether that function is increasing or decreasing or constant and what its extrema are. So let's start with like our standard mathematical definition for what these things are, these increasing, decreasing, and constant. What do those mean? Just drop this in. So function f is increasing on a given interval if for any 2 points on the interval, a positive change in x results in a positive change for f of x. What in God's name does that mean, Mr. Kulik? Here's the way that you'll think about it. Okay? You have a graph. You imagine like a little man that starts on the left side of the graph and walks to the right. As he walks along the graph, when he's walking uphill, that's when the graph is increasing. When that little man is walking downhill, that's when the graph is decreasing. Always from left to right. And when he's walking on flat ground, that's where the graph is constant. That's what we'll need to use this to do, right? So let's just take a look at an example and run through how to do this. Yep. Constant is flat. Yeah, that's it. So we're going to look at 2 examples here of doing this. We're going to write the intervals of increasing, decreasing, and constant. So let's start at the left side of our graph. So there's our little man, right? It looks like to me we're going to be walking uphill all the way till we get to here. Everybody agree with that? Okay. So if I look at the x-axis, that's the part of the graph where we're increasing. The part of the x-axis that corresponds to the graph where we're increasing, right? I'm going to use that part of the graph to write my interval for increasing. So we're starting with the left end of the graph. That's negative infinity. And we're going all the way to here, which is at -4. And then intervals of increasing, decreasing constant are a little bit easier because they're always going to have parentheses. Everybody's okay here? And then the next section, our little man's going to be here. That looks like constant. So looks like we're going constant from there to there. Oops, that's not the one I wanted to grab. So along the x-axis, that looks like it's from there to there. So if I looked at starting at x equals -4 and ending at x equals +3, and again, increasing, decreasing constant, all parentheses, all the time. Does this feel okay? It's very easy when we think about it, like you remove the mathematical definition, just kind of like, what does this mean visually, right? And we got our next section, our little man looks like he's walking down the hill. So it starts downhill here and goes all the way. So we started at positive, let's highlight the x-axis maybe. So they were talking about this part of the x-axis, starting at +3 and going on to include that right arrow, so positive infinity, and all parentheses all the time for these problems. That's it. Oh, that's not so bad, right? Let's look at part B here. So here, instead of giving us the picture, they gave us a function. What's the first thing I'm going to do? I'm just going to graph this thing on my calculator so I have a picture to work on. Yeah, absolutely. Yes, sir.
Decreasing. It's going right.
If you walk from left to right, you're going downhill, right? Correct?
So why is that positive?
Because you're it's covering the right part of the x-axis. Mm-hmm. So again, the intervals of increasing, decreasing constant are always describing the part of the x-axis that this happens on. That's why I highlighted below it. So it's just like taking that part of the number line and writing an interval for it. Does that? That's why I like starting with the number line stuff, because it just keeps coming back over and over and over again. So it's like the same thing, which typically we like. Oh my goodness, look at this crazy looking thing. All right. So let's get our little man. He starts over here on the left end of the graph. We start walking from left to right. We're going uphill, correct? So we're starting at the far left. So that starts at negative infinity. And we continue going uphill all the way to, looks like -3. Yeah. Again, that's where the asymptote is, because I see that -3 would give me a 0 denominator. Okay. And now I'll jump down to this part of the graph, right? So we're starting at -3 here. And if we walk from left to right, we're going uphill all the way till we get to, looks like x equals 0. So I'll do a union, and then I'll do -3 to 0. Question, why didn't I just write it this way? Does that mean the same thing?
No, because you're going on the x-axis. Across the x-axis.
Right, but if I go negative infinity to -3 and then -3 to 0, isn't that just the same thing as going negative infinity to 0?
No, because it's going to be the jump.
It's an infinite. Right, but does that matter?
Because it's all one graph, right?
So yeah, you got the right idea, I guess. So if I think about this based on the definition of increasing, it means if I wrote it this way, it means I should be able to take like this point from this arm and this point from that arm, and the y value should increase because the x value is increased, but they don't, right? You have to treat it as two separate intervals because of that. So if there's a break in the graph, if there's a discontinuity, you can't lump it all together as one interval. You have to write it as separates. That's the takeaway from that. So that wasn't right. All right. Next section, we're right here now, correct? And we continue walking and we start downhill. So that looks like that happens from 0 to 3. And now we know we have to end the interval because we hit a discontinuity. So we jump up to the next spot here and start walking from left to right. And we're decreasing that whole way, starting at positive 3 and going on all the way to the right. So positive infinity, yeah. We see them a lot. Yeah, I like it. Okay. All right. So that's increasing, decreasing constant. That's the gist of that. That's not bad, right? We can do that. Let's take a minute here and just stand up and stretch out. We've been sitting for a minute here now. A picture of me?
No.
Oh.
My boss. My boss is his uncle.
My boss is his uncle.
I work on Sundays at 9.
Okay. All right, stand up.
2 to 7.
Reach for the ceiling.
Oh
my god. Dude,
Stretch them out to the sides. Get as wide as you can.
You're about to faint. Stand up.
Find those toes.
Hands are so great. I don't like that. It's like sand.
All right.
Alright, guys, take it.
Oh, do you feel it?
Little twisty twisties.
Crack your back. Crack your back. Crack your back.
No, I don't
Trust me, I swear to God. Edge, you're gonna stop. How good am I at cracking back? Look at it. I promise. I promise.
You crack my back.
Ready? Breathe in.
I want you to fix my
You hear that though? Yes, sir. That is enough.
All right. Next up, we need to talk about extrema. So when we talk about extrema, there's really two kinds. You have maxima and you have minima. And for each of these, there's two types. You have local, and then you have global, or sometimes people refer to this as absolute. You could use those two terms interchangeably. Okay. So what's the mathematical definition here? We have a lot of words, which is never a good sign, but that usually also means it's going to be something simple at the end of the day, right? We say a maximum of a function f is a value f of c, so it's a y-coordinate, that is greater than or equal to all other range values of f on some interval containing c. We call this a local maximum if there are other range values that are greater than or equal to f of c outside of our interval. And we would call this an absolute or global maximum if there are no other range values that are greater than f of c. And then minimum is the same thing, except it's less than, right? So basically all we're saying is a maximum is a relative high point in the graph. It's local if it's the high point in its neighborhood, but there might be stuff higher than it elsewhere. And it's global if it is the highest point of all the points, or lowest of the lowest. So let's draw a little picture, and we'll just kind of identify, or like just practice the vocabulary here for a second. There we go. Okay, good. Okay. All right. So just drew a little picture here. How many extrema do we see in this picture? How many total maxima and minima do we see? We should see 5 total, right? So I see 1, 2, 3, 4, 5 relative high or low points. Everybody agree? Okay, I'm just going to label these as 1, 2, 3, 4, and 5 respectively, so we have a way to talk about them, so I don't have to label them as like points and give them numbers. It just makes it less convenient. All right. Do we see any global maxima here? Anybody?
1 and 3 look to be like
Great. They're the highest relative. They're tied for first, so they both count as global maxima. If you have a bunch of ties, you can have a bunch of global maxima. They just have to be the highest relative point, and if you have ties, that's fine. Is it common to have ties? Probably not, but I wanted to do an example where that happened. Okay. Do we have any local maxima? We usually, if we're counting global, if we're asking for global and local, yes, every global technically is a local, but if we're asking for global and then local, we probably don't need to count 3 and 5 also, or 1 and 3 also. So just 5. So the way to think about it is like in this little neighborhood, 5's the highest point, but there are higher points outside of that neighborhood. That's why it's just a local. Do we have any global, or do we have a global minimum? No. There is not a global minimum because there's always a point lower than any point you've chosen because the graph is going down forever. So we would just say there are no global minima. But we do have 2 locals. We have 2 and 4 are both local.
Wait, how do we know if it's a local or not?
So if there's just like a neighborhood that it's the relative high or low point, but in this case there's points lower than it still, that makes it a local. It can't be global if there's still stuff that's lower than it. It just has to be the best on its block, but maybe not the best in the city. You know what I mean?
And this is like number 5 a local because 1 and 3 are tied for global.
Yes, because there are points higher than it. Specifically, 1 and 3 are higher than 5. Exactly. Feel good? All right. Let's do one more example here, and that should probably wrap us up for today. I think is where I stopped in the other class. Getting everybody on the same page is always the goal every week or so. Let's make sure everybody stops at the same spot again. Yeah. Perfect. So here it says for the graph, f of x equals yada, yada, yada. Use your graphing calculator to find any local or absolute extrema and determine any intervals of increasing or decreasing. So it says to use our calculator. Let's fire that up. I'm going to go ahead and press the y equals button and probably want to look at the graph to do this, right? So I'm going to start just by typing this in. To get these bigger exponents, the easiest way to do that is to use this caret command. So above the division button, you have this like up arrow. You press that, and then you can type in like the number 4 or 5 or whatever you need. But make sure you press the right arrow after it before you start typing again, so you can move your cursor back to the main line so it's out of the exponent. Once you have that typed in, go ahead and hit graph. And if I look at this, looks like I see 3 extrema, right? I see 1 global minimum, 1 local maximum, and 1 local minimum. Okay. And now I'm going to want to get the coordinates for those 3 points. I'm going to do this using the calculator. The calculator can find the coordinates for these points for us relatively easily. If you have your graphing calculator with you and you'd like to follow along, you're welcome to do so. If you just want to sit and watch, that's fine too. Remember, with the video, you can always scroll back to the end here and rewatch the buttons that I'm pressing. If you get to the homework and you're like, yo, I don't remember what buttons did he do to do this, you can always go back and watch. All right. So I'm going to start by pressing the blue second button and then pressing this trace button at the top to access the blue command here that says calc. That opens up the calculate menu. These commands all are used on the graph of a function. So if I read through these and I'm looking for these maxes and mins, which commands sound like the ones that I'm going to be interested in using? Minimum, maximum. Yeah, shocking there. So let's find this global minimum first. So I'm going to go ahead and move down and press the minimum command and press enter. So now the calculator is going to ask me a series of questions. If you look at the bottom of the screen, it says left bound and a question mark. So the calculator wants me to choose a point somewhere to the left of what I'm looking for. So I'm going to go move my cursor over so that it's somewhere over here and then press enter. I see my cursor flashing right there. So I'm just going to use the left and right arrow keys to move my cursor along until I'm somewhere over there. Doesn't really matter where I'm at over there. This looks good to me. I'm going to press enter. The calculator now asks me for a right bound. So it's asking me somewhere to the right of my minimum. I'm going to pick some point on this little section of the graph here between the min and the max. So I'm just going to scroll over there. That looks good. I'll press enter. And now it asks me for a guess. Let me tell you a secret. The guess doesn't really matter. Like, will it find your answer a little bit faster if your guess is closer? Sure. But like the difference is going to be like microseconds between just picking anything inside of your bounds. I always just press enter one more time and just use my guesses to wherever I ended at. And here's my answer. So negative 2.242,682, comma, negative 9.653,029. Yikes, that's a lot of decimals. Let's just round those to 3 decimal places. Sound good to you guys? Everybody happy? All right. So let's go back now. Let's find our local maximum here. So I'll press second and trace to go back to that calculate menu. And this time I'm going to choose the maximum command. The calculator is going to ask me the same 3 questions, left bound, right bound, and guess. So the left bound, I'm going to pick some point over here, left of that maximum. So that looks good. I'll press enter. Right bound, I'm going to pick some point over here between the max and the min. So move my cursor over. That looks good. And a guess, I'll just guess where I'm at. So there's my local maximum. Again, I'm going to take those decimals and round them to 3 decimal places because woof, that's a lot of numbers to try to write down. Okay. And then one more minimum, so second and trace, minimum command again. Same 3 questions, left bound, right bound, guess. I'm just going to do that real quick. At this point, I hope you guys got the gist of like how to do that on your calculator. It's not too bad. Again, rounding to 3 decimal places because too many numbers. Everybody happy how we use the calculator to get those values? I take it you probably did that last year in your Algebra 2 class, but if you didn't, that's how you do it one more time. Yes, sir?
Can you show how to do the balance again?
Yeah, so that it just comes up automatically when we select the commands. So if I'm looking for, say, this minimum, the left bound needs to be some point over on the left side of that minimum, so somewhere over here. So I'm just going to move my cursor, which is currently located here. You see the little guy flashing? I'm just going to use the left or right arrows to move my cursor over to where it needs to be. So anywhere over here is fine. So I'll press enter. Now it asks for a right bound, so I need it somewhere on the right side of my minimum. My minimum's right down there. So I'm going to pick something along here between the minimum and maximum. So I'm just going to move my cursor over there somewhere. So that looks good. And then press enter. And when it asks for guess, I just guess wherever I'm at. And then, boop, out it goes. That cool? Okay. All right. There's another part to this question, though. It also asks us to determine any intervals of increasing or decreasing. So let's go back and look at our picture here. So imagine our little man is starting on the left end of the graph and starts walking. We're going all the way downhill until we get to the global minimum, correct? So the x-coordinate on that global minimum is going to be the end point of that interval of decreasing. So we start at negative infinity, and we ended our decreasing when we got to that global minimum. Everybody's okay with that? At that point, we start walking uphill. So we go uphill from our global minimum all the way till here, which is where our local maximum is. So we're starting at our global minimum, and we're ending when we get to our local maximum. Oh my goodness, guys. I just wrote those in the wrong spot. My apologies. Okay. That's more like it. Yikes! Almost made a bad mistake there. Okay. So now we're up here, right? So we continue walking to the left. So we go downhill all the way to the local minimum. So we're back to decreasing here. So we started at the local max, and we went all the way to the local min. And then now we're here. We continue walking to the left, so now we're going back uphill again. And we're going uphill forever. So starting at the local min and going uphill forever. So it's nice because the endpoints for my intervals are always going to be the x-coordinates from my extrema. right? That feels like stopping time to me here, folks. At this point, you guys can now do up to number 18. So that'll be the last problem for Sunday's problem set, will be to 18. Anything that we assign on Friday past 18 would be for the following Sunday's problem set. We've also done now quite a few sections. Remember, every chapter there's going to be an unannounced homework quiz. Might be getting pretty close to time for one of those. So just as an FYI,
Friday.
might be a good day to try to do that. Again, the homework quizzes are unannounced. They're closed book. They're based on recent homeworks. If you've done the homework up until that point, you should probably feel pretty good about whatever I ask you to do. Okie doke. But just a reminder that that's coming at some point this chapter, at least one time, typically just once. But if you haven't gotten caught up on your homeworks, you may want to make sure that you've looked through that stuff enough that you're like, okay, I think I can do this.